For this webinar, I will talk about raw earth in construction. So we will go through a series of examples of buildings, the history of this technique, a lot about the soil used in this technique, and then a little bit of innovation related to this topic. So just an overview of the contents that we will go through. There will be a brief introduction, then an overview of the main techniques used in earth construction, an overview of the history of architecture made in earth, and we will go through examples from all over the world. A chapter about an example of earth buildings that are the Fujiantulo in China, which are a really good example of raw earth construction resilience. A few examples in the modern times to show that actually this technique is still very much used and can be modern as well. The main part will be about the soil, because of course it's the main material used for this technique. So we will go through its characteristics and testing and soil stabilization as well. And then the last part about the innovation and how raw earth can really help to help buildings to reach net zero, so an innovation part. So we can start with earth construction. So it's been a bit of an overlooked technique. It might seem a bit rudimental, but it's actually very widespread. It's been one of the most used construction materials by mankind, and because of its availability and immediacy of application, it's been always used by man since mankind started to build homes and settlements. And today is quite surprising that more than a third of humanity lives in a home built of earth, from all over the geographical parts of the world, and there's quite a range of types of buildings made in raw earth, from very simple buildings to quite large and complex structures. So this is an overview of the main techniques. So the techniques reflect, of course, the local knowledge and local culture. The most commonly used are adobe. So these are sun-baked earth bricks, often added with straw to give more structural stability. They are traditionally shaped by hand. And they are in a wooden or metal, made in wooden or metal frames. Another technique is rammed earth, or pise, also called. This is made to build walls. So the earth is poured into a formwork, and here is rammed. Historically rammed by hand, but now the process has been mechanized, which is much faster and efficient. Straw clay is a technique where the earth used is very clay rich and with lots of water, so to make a slurry mixed with the straw. And this technique is commonly used to make prefabricated elements. So depending on the mold that is used, a series of elements can be made. Wattle and dop is a technique where there is a structure. It's made of plant fibers or wood. It's like a grid or a lattice, and then earth is mixed with straw and is applied to the lattice by hand, so that like a sort of panel is made. Direct shaping, quite obvious, but it's also very used even in large structures. So basically the earth is quite plastic in this case, and it's literally shaped by hand and applied directly on the structure with the desired shape and form. Then we have compressed earth blocks, so quite similar to the Adobe technique, but more mechanized and modernized. Today, usually hydraulic presses are used to make these blocks. And this technique also offers a wide flexibility because depending on the mold that is used, a range of dimensions can be produced. And finally, cob, also quite common for raw earth houses. So the procedure consists of stacking earth balls. So also these are made by hand, and then they are applied to the walls and to the structure. And also here is quite common to add fibers into the mix to give that structural stability. So this is an overview of the main techniques, but now we go into the history of earth construction. We will go through a few examples from all over the world. So we start from Africa. So the history is quite ancient. We go back to the times of the Egyptian, so 3000 BC. And of course, the Nile Valley was the main location where earth building, earth construction thrived, because of course the soil found in the Nile Valley is suitable for construction because is rich in clay. And it's also rich in sand. Sand was widely available from the neighboring desert. And the straw was added from the cultivated grains. Of course, firstly, it was shaped by hand, and then molds were used when the technique was more developed to make unbaked bricks. And here we see an example of raw earth architecture. This is the Thebes with its necropolis in Egypt, and this is also a UNESCO World Heritage Site. Here we're still in Africa, much later, so we are in the 11th century, but with the expansion of Islam, of course, the architecture developed and changed. The architecture of the mosque was introduced, and they were built in earth with techniques locally available. Here in this example, this is the Great Mosque of Djenné in Mali, and it combines various techniques, but it's made of sun-baked bricks on the inside, and then it's plastered with earth as well, with some direct shaping technique, and it's quite an interesting example. And then we move to Europe. So the oldest settlements found date back to the 6th millennium BC. There were these primitive dwellings in Greece, and they were made of a combination of wood and earth. And basically, earth was mainly used for houses, for residential houses. Few examples of public buildings made of earth, but here in the picture we have the North Portico in Knossos, and this is one of the few examples where earth was at least part of the techniques used to build it, in combination with the local stone and also lime mortar as well. And still in Europe, we have quite a few points. So during the Roman times, earth brick walls were built for sacred and public buildings. But also during the Roman Empire, sun-baked bricks were used to build modest houses and dwellings for the poor, while the richer palaces were made of stone and clay bricks, fired bricks. But despite this, the technique of building in raw earth was actually praised by Vitruvius in his book. And we know that this technique was known to the Romans and used, but for more modest buildings rather than high state palaces. And in the Middle Ages, this technique was a bit left. It wasn't used very much. There was a resurgence in the 18th and 19th century. And then, interestingly, in the post-war times, so in the 1950s in Europe, raw earth was used more for buildings because of the urgency to house thousands of homeless people, and also because there was a scarcity of materials. And since then, unfortunately, this technique was not so used anymore. Other techniques were preferred that felt more modern. But in the last probably 20 years, raw earth has been more appreciated and debated and discussed because of its resilience and sustainability advantages. And in the picture here, I put a modern example. So this is the warehouse of a big corporation that makes like cosmetic products, and one of their main warehouse is all made in rammed earth. We will see more pictures later, but this is quite a clear example that this technique is still very relevant and used in the contemporary times. Now we move to West Asia, where we have here an example in Iraq. This is the city of Nineveh, and is known for its massive walls built in raw earth bricks. Then we move also to Central Asia, so in India, where in Antiquity the people there lived in dwellings built in unbaked bricks. And this, in the picture, we have the example of the archaeological site of Mohenjo-Daro, which was built on two mounds, both made in raw earth. On the eastern mound, the houses were built in earth brick internally, and then they were faced with oven-baked brick outside to provide that extra protection. And then we move to East Asia. During the Shang dynasty, rammed earth was used to make buildings above the soil, while before only kind of dugouts were made, so underground houses. Otherwise, other techniques were used. And here we have an example. So this is the Great Wall, and many sections of the Great Wall were built in rammed earth. We can see the characteristic layers of this technique in this picture here. And then we move to America. Again, raw earth very much used throughout time. Very, very common and developed technique. A big example is the Pyramid of the Sun. It's a massive, massive structure, all built in rammed earth. In Tenochtitlan, the residential districts again were built in houses made of earth bricks and then covered with a kind of lime plaster. And then big example in America is the architecture of the pueblos. They definitely mastered the technique of the earth brick. So they would build the walls in earth brick and then render the walls with earth mixed with finely chopped straw. Or they would make balls of earth and pressed and smoothed by hand. And the roofs were covered with brushwood and finished with rammed earth. And in this picture, we see an historical site, which is also quite touristic. So this is the original, but even nowadays, like modern buildings are still built with this characteristic technique in the area of southern US, so New Mexico and Texas. This technique is very, very common even for modern buildings. And now I wanted to put a bit more focus on this type of building. It's called the Fujian Tulou, and it's quite a good example of how resilient buildings in raw earth can be. So we are in Fujian. It's a region in China, in the southeast of China. The Tulous are these large earth buildings, and they were built between the 15th and 20th century. We can count more than 4,000 of these types of buildings, which would house thousands of people. So this is the most ancient type of Tulou. We will see other type in the next slides, but this is the square plant type, and it's the oldest, but it has some weak points. For example, having corners in the structure that would provide a point of weakness. So that was developed into this type of structure with a round plant. And you can see each section involves a bigger part with many stories and then a smaller home on the side, which is more on the central part, more towards the center of the structure. And this is the classic characteristic Tulou building. And this is from an external point of view. So there are these agglomerations of Tulous with both round and square plant, and they would provide housing for many people. And because of their shape, they would foster a sense of community. So it would be good even on a social point of view for the local people, actually. And then in terms of the architecture and engineering side of this building, we can look at the tie systems. So this is actually the main contributor of why these buildings are so resilient, especially to earthquakes. Between the layers of the rammed earth in the walls, they would put these wooden logs and reinforcement, which would give more structural stability, but would also provide flexibility and would accommodate movement. So this type of technique is really advantageous for that. And then we can look at the roofs and we can draw some lessons from this element. So the roofs, first of all, they always have generous eaves, which would provide protection from the weather, from moisture, from rain. The roof is an independent element from the earth walls. So this is also advantageous in terms of earthquake resilience. And all in all, we can see that more focus is provided to protection from shrinkage and focus on drainage, not only on compressive strength and general strength of the material, but really a focus on accommodating movements in the structure. And finally, when we look at the windows of these types of buildings, we always see that they are rather small. And this is done because having small windows can provide more strength to the overall structure. They would keep lower stories more solid, and really small and well-distributed openings were preferred rather than few big windows. Here we have a bit of a demonstration of how traditionally rammed earth walls are built. I'm not sure if the audio will work, but I can talk on top of the video. So yeah, we can see here, this is the traditional process. Now it's mechanized, but we can see the two people are standing on top of the upper layer of the wall. The foundation is built in stone, and then on top of the foundation, the formwork is placed, made of wood. Then the soil is, or the earth is poured into the formwork. And then the workers have this tool, it's called the rammer. And then they would start to manually ram the earth to compress it. So layer by layer. And we can see that it's quite a labor-intensive process, definitely. Again, now it's mechanized, so it's much quicker and efficient, but this is how it was made traditionally. And even with this labor-intensive process, quite big buildings could be made. So yeah, this is another view of a construction site of these types of building. So we can see the gradient in color from the bottom layer where the earth is dried and then gradually is more wet. And we can see that layer by layer the walls are constructed. So these wooden parts is the formwork, which is placed on top of the wall, and then another layer is placed and rammed and compressed. And here on the right, we can see, so we have the circular plant, then we have the foundation made in stone, and then layer by layer, the earth is placed and compressed to have the full height of the wall. Now we have a look at a couple of examples of modern architecture made in raw earth. This is a dugout in Switzerland. Dugouts is really one of the first example of house made in raw earth is excavated in the soil. This type of structure is mostly concentrated around the Mediterranean, so Spain, North Africa, Greece, Italy. But it can also be a modern structure like this one in the picture. And in quite a variety of climates and conditions, because definitely Switzerland doesn't have that Mediterranean climate, but it still can be used for these type of structures. And then we're back again to that building made in rammed earth in Germany. We can see here parts of the construction site. We can see that the formwork used is wooden, and we can see that this technique allows to make rounded walls as well. Here we have an opening for a door. So the type of formwork is really important in the rammed earth technique. It needs to tick a few boxes. It needs to be solid and stable, of course, but also very importantly, needs to be easy to assemble and dismantle. Needs to be flexible to accommodate different heights, length, and thicknesses. And it can be made in a range of materials. So traditionally it has been made in wood, but also logs, aluminium, steel, and glass fiber. And again, it allows to make curved surfaces, which is quite a particular feature. And yeah, traditionally it was earth was rammed manually, but this was extremely labor intensive. But nowadays it can be made mechanically. And the most common type of rammer is the pneumatic rammer, which is definitely by far the most effective, efficient, and it produces very high quality results. This is another example of a modern building made in rammed earth. This is a modern church and community center, I think still in Germany. But this is the construction phase. Here the workers are removing the formwork, and we can see the fresh wall made of rammed earth is still dark because the soil is still wet. And here we can see the finished building from the inside. So the internal walls are as well made in rammed earth, and we can see that the result is quite aesthetically pleasing, but also very resilient, and also it provides very good thermal efficiency because it keeps the indoor cold in summer and hot in winter, so very good for that as well. And now we can move to the soil section. So we will explore its composition, its main properties, and some stabilization techniques. So we start with a bit of an introduction, how soil, what soil is made of, what's its profile. So here we have a bit of a schematic, and on the side here, this is a picture of a cross-section of a soil. So on top we have an organic surface layer, and then we have the topsoil, which is a mixture of organic and minerals. There can be some discoloration due to alluviation. So basically the rainwater comes in from the top, and then it drains down to the most inner layers of the soil. And with that, the water dissolves some of the minerals and carries them towards the core of the soil. For example, in the picture, we can see examples of this discoloration. For example, here, probably the rainwater took some of the minerals from here and carried them to the deeper layers. And we go down to the subsoil, where we can find less organic material and more minerals. For example, iron and aluminum oxides are very common. There is accumulation of clays and ferrous oxides that are carried by alluviation. So the water carry the mineral and deposit them in this layer. And then if we go even deeper, we have the substratum. This is crushed or cracked material from the bedrock. This is chemically identical to the bedrock. This is poorly weathered or unweathered, and then even deeper we have our bedrock. So water is quite important when we're working with soil and especially raw earth techniques, because water has quite obviously big effect on the soil properties. It imparts cohesion to the soil. Suction is exerted by the soil towards the water by capillary forces. Water in some soils or in most soils gives an effect of swelling because of the clay minerals contained in the soil. Upon drying, there is then shrinkage, so a volume decrease, and water imparts plasticity to soils. So quite a range of effects and property changes. And then we can find soil in a variety of states. These are also used, most of these are used in different raw earth construction techniques. For example, in some techniques, we want to use slurry or mud, so a more soil much rich in water. While for other techniques, we might want a semi-soft or soft paste to be more moldable, while for other techniques we want even drier soil. For example, in rammed earth, we want a bit of moisture, but not that much. And then we have a series of soil components. As we've seen before, we have organic matter, especially at the surface. We have a range of minerals that can be unweathered or weathered, and these minerals are mainly silica. These are the quartz grains that are produced from the disintegration of sandstone. And this quartz resists chemical weathering. So quartz grains can be as small as clay, but still the chemistry is the same as the original quartz, and these are not these cannot be weathered, and also they are not reactive if we use a stabilizer. Then we have our silicates, so mica, feldspar, and other silicates, and these are subject to weathering and can form clay minerals and are more reactive. And then in some soils we have also limestone or other calcium carbonate based rocks, and these are subject to acidic dissolution, so we can have another range of properties. And then if we look at the grain size distribution, we can have a range of particles, so from pebbles to gravel, sand, silt, clays and colloids. So here the difference between clays and colloids is that clays are a particular type of colloid. They are fine-grained, but also they are actually clay minerals, while colloids, we include any particle below 2 microns. So this can be also quartz, very fine quartz, or limestone or magnesium, which are not properly clay minerals, but they are fine-grained. So here we have just a reminder of the classification of silicate minerals. This is quite relevant when we're dealing with soil in earth construction. We will skip through this because I'm aware of the time. We have a range of clay minerals. They have different properties, but most importantly, we want to look at the swelling properties. So, for example, if we have a soil that is quite rich in montmorillonite, then we will have a strong swelling. So we need to be aware of that before using it in construction. But also we need to be aware of the properties of the clay minerals in terms of bonding, because some minerals can be more cohesive, some can be more plastic, So I put here a table with the most common clay minerals found in soil and their relative properties. Then when we use soil in construction, we want to have a range of field tests available so that when we are on the site, we can choose the soil on site and have like a sort of preliminary test. So we have an idea of how how this soil will behave. So they are very empirical, quite rudimental, but very useful to have an idea of the type of soil. So just like touching or cutting the soil with a knife and see how shiny it is. So this type of very simple test, but very useful to see what's the texture, how plastic it is. It's very useful. And then in terms of properties, we have actually four main fundamental properties of soil that we want to study before applying it in a project. So we have the texture, which is the particle size distribution, the plasticity, the compressibility, and the cohesion. And for each of these properties, we have dedicated actual tests. So we will go through them quickly. So texture, we know particle size distribution. There are a couple of standard tests, both British standard, but also ASTM standards. They classify the grains based on their size. And the test combines a few techniques. So for the coarser fraction, we use dry sieving. And then while we go to the finer fraction, we will use wet sieving. And then for the clay fraction, silt and clay fraction, we use the sedimentation test, which can be carried out either through a pipette method or through the hydrometer method. Usually the pipette method is more accurate, but it's might be more difficult, while the hydrometer method is a bit easier and quicker to do, but it can be less accurate. This is an ideal particle size distribution of a soil applied in earth, but again, the particle size distribution need to be kind of studied case by case based on the application mostly. And also, yeah, and in general, a soil suitable for raw earth construction has between 20 and 40% of clay and silt fraction. But this depends again on the application really. Then when we study the soil plasticity, there are the Atterberg limits that help us in identifying the type of soil in terms of its plastic behavior. So in this graph, we can see that we have on the x-axis, the x-axis, the water content, and then on the vertical axis, we have the volume. So when the soil is completely dry, it has, of course, it's in a solid state, but we can increase slightly its moisture and the volume won't change. This means that the soil is still not saturated, and then it will reach its shrinkage limit, this is called. And this means that here the soil is saturated with water, and as we add more water, the soil will start swelling and increasing in volume. And then we will reach a point where this is the plastic limit. The soil will start to have a plastic behavior, so it can be modeled and shaped. And as we continue to add water to the soil, we will reach the liquid limit. And at this stage, the soil will have basically a liquid behavior. So to identify these limits, which means at which water content the soil will have which behavior, there are a series of tests. Now we will have an overview of these tests very quickly, but there is much more content and sources that I can give at the end to read more in detail what these tests are. So to identify the liquid limit here, we have two methods, the Casagrande apparatus and the cone penetration method. Basically, we take a soil with a certain amount of water in it, and with this machine, we apply 2 blows to the sample of soil. And the limit is when at 25 blows, the soil combines here in the middle for 12 millimeters. Now, of course, it's very hard to find the exact amount of water that will yield this situation. So when this test is carried out, it's repeated on a number of samples with varying moisture values, so that we can build we can build our line, and then we can extrapolate the value of the liquid limit. And similarly is done for the cone penetration method. So this is our soil sample, and this part of the machine is left for free falling on its weight. And depending on the moisture, this cone will penetrate a different depth. But the liquid limit is when the cone can penetrate for 20 millimeters. So again, it's very hard to get the 20 millimeters exactly. So same approach, different samples with different moisture. We build our calibration curve, and then we extrapolate the value for the liquid limit. For the plastic limit, the test is really simple. A moist soil sample is taken, and then we need to make it into a thread of a 3 millimeter diameter. If the thread crumbles before attaining 3.2 millimeter, then this means that the soil sample has reached its plastic limit. And then for the shrinkage limit is a bit more complicated, but very simple, actually, just complicated to explain. But anyway, so this test is, we take a sample of the soil of a known volume, and this is saturated with water. So there is a part of dry soil, we call it, with a certain amount of water, and we call it the initial amount, the initial water content. Then this sample is dried in the oven until it's completely dry, and this is the state of the dry sample. And we assume that its volume, we call it volume dry, and we can measure it either geometrically, or if we have a lab and we can measure the envelope volume with an instrument, we can do that. But we assume that the volume of this soil is the same volume as the soil at its shrinkage limit state, because if you remember, we said that when it's not saturated with water, the soil won't increase in volume by adding more water. So with this assumption, we can calculate with this formula the water content of a specific soil at its shrinkage limit state. And then eventually, when we have identified all these limits, all these water contents in the soil, we can plot them, and there are tables available where we can say, okay, my soil has this specific liquid limit and this plasticity index, and I can plot it, and I can define if it's a low plasticity clay, low plasticity silt, or high plastic clay, high plastic silt, or etc. So to interpret the results of the tests. And then we can also measure the compressibility of the soil. This is the Proctor test. So this is to identify the optimal moisture content for a soil to be compressed. So basically, if we want to compress a soil, for example, in rammed earth, we need to identify what's the best water content that can help us to compress that soil, and the Proctor test is aimed at finding that water content. Now I have only little time left, and I really apologize for this, so I will skip through a bit of slides because I want to get to the final part where we talk about soil stabilization. So this is the cohesion test. It's basically a wet tensile strength test, and this is also to understand how cohesive the soil is. And then we can do more advanced analysis on the soil prior to application. Mostly it's XRD and XRF analysis to identify the elemental composition and then what clay minerals are contained in a soil. And then, yeah, for soil stabilization, so basically we can have three main approaches, but the third approach is to modify the local soil to make it better suited for a specific project. So we want to modify its properties by different means. So we can modify the properties of a soil with mainly three methods. By mechanical stabilization, so we can compact the soil, or physical stabilization, for example, by modifying the particle size distribution of a soil, or by chemical stabilization, so basically introducing an additive, which can be cement or lime, but also fibers, bitumen, resins, glues, or commercial products. But in this case, we will focus on soil stabilization with hydrated lime. It's because it's what we do at our company, and also it's a very wide technique that it's been used in history to stabilize soil with slaked lime. Slaked lime binds the soil through to two main mechanisms, which are carbonation and pozzolanic reaction. So carbonation, it's because slaked lime will react with atmospheric CO2 and transform it into calcium carbonate. So this is a weak type of cement. And this reaction consumes part of the lime available for pozzolanic reaction. While the pozzolanic reaction is definitely the most important reaction for lime stabilization. The clay mineral will dissolve in the alkaline environment created by the lime, and such silica and alumina dissolved from the clay will react with calcium ions from the lime, and this will produce aluminum and calcium silicate, which are the phases that actually impart strength to the material. So in order to be able to do this, we need to have a soil that contains a significant clay fraction with high contents of alumina silicates, silicas, and ferrous hydroxides. Organic matter hinders this type of process, so it's recommended not to use a soil that has more than 20% of organic matter, but the least the better, definitely. And the procedure for stabilizing the soil with lime, there are a few steps. So first we need to crush the soil with the lime, and the more finely the soil is crushed, the most it will be available to be attacked by the lime. So crushing is very important, as is important the mixing, because we want a very intimate mixing between the soil and the lime so that the two materials are in contact with each other and can react with each other. Sometimes a holdback time is applied And also the drying and curing can be advantageous. So curing at mild temperatures to around 60-90 degrees can promote the pozzolanic reactions. Um, so this is just to say that water has a significant effect on lime-stabilized clay soils. A series of tests can be carried out to evaluate the effect of lime stabilization. So we can actually evaluate how the stabilized soils can perform with respect to unstabilized soil, which is very important. And also I wanted to note that in the literature there is a lot about soil stabilized with quicklime, so calcium oxide, but there's not much about stabilization with calcium hydroxide, so slaked lime, which could be interesting. And then the final part is about innovation in raw earth and how this material can help towards net zero. So a bit of a background, I think it's quite well known how impactful the construction sector is on the environment. We all know how much cement production is impactful in terms of CO2 emissions, but also the construction sector is a high producer of waste, especially soil waste. So there are quite a lot of challenges that need to be addressed. And raw earth, if raw earth is more used in construction, I believe this will help to at least partly address most of these challenges. So what we do at Earth for Earth is lime stabilized earth bricks. These are advantageous for a series of reasons. First of all, they capture CO2 from the atmosphere because of the slaked lime in it. They are made of recycled soil, which is a lot. A lot of waste soil is landfilled, so we can recycle it in our bricks. They are just as durable and performative as clay-fired bricks. They are recyclable, and raw earth in general, not only our bricks, but in general, raw earth architecture is very resilient and very energy efficient, which is quite advantageous. A bit of innovation that we propose in our brick is the lime stabilization. Of course, lime production emits a lot of CO2 in the air, but we have introduced a new process to make lime, which doesn't emit any CO2. So traditionally, lime is produced by calcining the raw material. And of course, this emits CO2 for two reasons, both for the combustion of fossil fuels to reach the high temperatures, but also from the chemical breakdown of the raw materials. We have introduced a new way to make slaked lime. It's a chemical treatment. So basically, we react our raw material with the sodium hydroxide, and this produces calcium hydroxide and a byproduct that is in a solid form, and this avoids both sources of CO2 emissions. So when this is integrated in a raw earth system, really creates a system that is really sustainable, life cycle sustainable, with a negative impact on CO2 emissions. And yeah, so a bit of takeaways from today's webinar. I hope it was a bit useful at least. So raw earth is an ancient technique, but it's also very contemporary. It's still housing a lot of people in the world, and it's proven its durability across climates and cultures. There are a lot of traditional techniques that show very good performance, and when they are correctly detailed, they can really provide seismic resilience, but also moisture management and thermal comfort. Good earth construction definitely starts with the soil, so appropriate particle size distribution, moisture content, and compaction are key. Lime stabilized earth can turn excavated waste soil into a durable, recycled, and high performing building material. It captures CO2 and it reduces reliance on cement. And innovative lime production routes can shift binders from net emitters to net carbon sinks. This supports net zero targets, of course. So integrating these approaches at scales offers a practical pathway to lower carbon, resource efficient, and resilient built environments, particularly where large volumes of soil are already being excavated. So yeah, I hope. I also added the sources that I've used for this. So if